So I can share the PDF.
Yes, madam, please.
Okay.
Sir, you can pin the name Jyoti Lakshmi so that organizer, one of our organizer will listen to that.
Yeah, it once again it threw me out again. I will have to. Oh, come on, this is very strange. This never happened to me earlier. I do not know, Mr. Dea, what's happening. I cannot see anything at all. I cannot hear anything at all.
Professor, can you see Jyoti Lakshmi in your mobile itself? You can see Jyoti Lakshmi. You can scroll your screen.
Yeah, I see, and I have
down.
pinned her.
You can see Jyoti Lakshmi.
Yeah, I see, and I have pinned her.
Yeah.
But I still do not hear anything.
Yeah. Two names will be there. Jyoti Lakshmi M is present.
Yeah.
Jyoti Lakshmi M.
I see that, but I do not
another name,
hear
sir.
anything.
That also.
Now again it stopped me.
Okay.
Mr. Day, I'm very
Professor, no
sorry,
problem.
but it seems. Yeah. May I please request you one thing, because somehow it's there's some problem. It's not working. Feel free please to circulate
Yes,
the presentation which I sent to you. You can please send it to all the participants. And if there are any questions, then and someone writes to me, I will be definitely responding. I'm very sorry, but I tried my best and it's not working. So
sir,
maybe something like this we can do.
Name,
Professor, one more suggestion. Shall I give?
Yeah.
Professor?
Yes, I'm hearing.
If you are having your laptop, you can open your presentation there. You can present there. And you can read by seeing your laptop. And then if you finish every slide, you can tell us to change slide so that we will be changing. The participants will be seeing the presentation and you will be giving your voice, and the PPT from your laptop you can able to control.
Okay, so now I am
now it is in first slide, performance based seismic design.
You can see that, or
yes sir, we can see it. So that if you finish every slides, you can control us like next slide, so that we will be pushing the next slide.
Oh, okay. Just give me one moment, please. Are you able to see my screen?
Yes, sir.
You can? Because here I'm trying to share my screen, and now it is. It's again throwing me out of the meeting. I don't know what's the problem.
Professor, my idea will be very useful, I think. Just you can give your voice through the mobile. Using laptop, you can explain us about the PPT. You can just tell to move the slide so that we will move it. The participants will be seeing all the slides. It will be very convenient.
Good. Then, fine. Then let's start right away. So, okay, good morning, good afternoon there, everyone. And so my name is Akanshu Sharma, and I'll be presenting on the topic of performance-based seismic design and strengthening with focus on fastenings. I'm sorry for this trouble with the network and all, but let's try. I will try my best to go ahead and present. So we can go to the next slide. So here we see the contents, which so what I'll be presenting. So we will have some introduction, why we need the performance-based approach, what is the seismic performance of reinforced concrete structures, then how we can apply the performance-based approach for seismic strengthening, and in the end, we will talk about what's the importance of anchorages or fastenings in the strengthening, let's say, connections, to make the connections. So we can go to the next slide, please. So it's just the introduction, why we need the performance-based approach.
Professor, sorry for the interruption. Just a minute.
Yeah.
Professor, sorry for the interruption. Just a minute.
Okay.
I will give some instruction to the participants so that they will be very clear to understanding this. Participants, please pin Jyoti Lakshmi M, the name Jyoti Lakshmi M, so that the PPT will be coming from that name. Thank you. Thank you, sir. You can continue, sir. Thank you.
Okay, good. Thank you. So we can go to the next slide. So slide number 4. So here I would like to mention about the performance-based approach, right? So when we are learning about the design of civil engineering structures or reinforced concrete structures in particular, then on one side we have some very classic examples like shown here. For example, I think everyone knows this picture on the left hand side. This is for the Burj Khalifa, and on the right hand side is the Stuttgart TV tower, which is, let's say, the first TV tower to be made by reinforced concrete. So when we see these kind of structures, then we see, okay, there is what we are doing in the designs and all, which is correct, because otherwise these kind of structures we would not be able to construct in today's date. But if we go to the next slide, there we see some terrible examples also, which show that under the cases like earthquakes, for example, we have some very poor performance of the normal reinforced concrete structures, and that brings us to one strange question, that how can this be that with the same principles we can on one side design some very classic buildings, and on the other side we are still not able to, let's say, ensure the safety of reinforced concrete structures against earthquakes. If we go to the next slide, then we will see that although performance-based design is a relatively recent topic in the modern civil engineering, but if we look for the historical evidence, then we can find even in the codes which were written like 2000 BC, which was something like 4,000 years ago. For example, the Hammurabi Code, there it's also written a structure should not collapse and kill people, which is nothing but a performance criteria which a structure should meet. So if we continue, then we see that, so I will be presenting now something on the seismic performance of reinforced concrete structures. So if we go further on, there I will be presenting like if you have a reinforced concrete frame structure and it is subjected to lateral, for example, seismic loads, then there are different stages through which the structure goes through before collapse. So in the beginning, if we apply a small displacement or a push, then we have more or less like a linear force displacement curve, or the base shear versus roof displacement curve. We have more or less like no or minor non-structural damage in the structure, and there are no permanent deformations. So if we remove the load, the structure should come back to its original position. This kind of a performance level is known as the operational performance level. If we go to the next slide, slide number 9, then we go to the next level of performance where we start to see some small damage, so limited damage in some non-critical locations. We see a slight change in the slope of the load displacement curve, which is, let's say, associated with the change in stiffness, and therefore we get then some permanent deformations if we remove the load, but still the damage is rather limited and we can repair that. In most of the cases we can repair it well. This is what we call as the immediate occupancy, because that means that even after the earthquake, immediately we can reoccupy the building. If we go to the next slide, there we see what happens if we further keep on pushing the structure. So if we push it further more, then we see that we have significant damage at various locations. The displacements are progressively increasing. The structure, if we now remove the load, then of course there will be large permanent deformations. We may or may not be able to repair the structure anymore, but there will be no threat to life safety. So this is known as the life safety performance level. And normally the peak of the load carrying capacity of the structure comes at this performance level. If we push it further, if we go to the next slide and we push it further on the structure, then we see that there is large damage at various locations, and also critical locations. The loads start to drop down, and this means that there is large damage. There are large permanent deformations if we now remove the load, and the structure may not be able to sustain any more further um, lateral push. So if there would be an aftershock after an earthquake, then it might collapse under that, and the only stability would be against the vertical loads. So this is what we call as a collapse prevention. So this is the absolute limit beyond which we cannot allow the structure to go in any circumstances, because then it would definitely collapse. So if we go to the next slide, in slide number 12, what we can see is that from the point where we get the first damage or the first crack in the structure until the point of collapse, there is a large, let's say, gap. There are several stages through which a structure goes through, and this means that and the load remains more or less constant beyond a certain point, which means that load carrying capacity or the strength of a structure cannot be a criteria, because for the same strength we can have several different displacement values. So what we can see here is that performance of a structure is somehow related to or proportional to the displacements which are taking place in the structures. So that means if we want to talk about the performance of the building, then we can only do that if we start thinking in displacement domain instead of force domain. This, if we now go to the next slide, this also is a classic example which shows whether it's really even feasible to design for strength against earthquakes or not. So this is a famous example of the collapse of the flyover or the bridge during Kobe earthquake in Japan, where the very heavy columns were used from the principles of strength-based design, and it was seen that once the strength is exceeded, then the structure is definitely going to collapse without any, let's say, without any warnings. So this is the thing which we want to avoid. We do not want any brittle failure in the structures. If we go further on, then we go to so this is something what we call as the moment distribution method. So or let's say the typical bending moment diagram for a reinforced concrete frame structure under lateral loads. If we ignore the gravity loads, then it would look something as shown in this figure. And there, mostly if we have to do it with the hand, okay, normally nowadays we are doing all this analysis with computers, but if we would have to do the analysis of the frames using hands, then we would typically use moment distribution method. What's interesting is that the inventor of the moment distribution method, which is basically a force-based method or actually a stiffness-based method, said that strength is essential but otherwise unimportant. And this is what we just saw in the previous slide, that once you reach the limit of the strength, or let's say sort of a yield limit of the strength, then you only have large displacements without any further increase in the resistance from the strength point of view. Now, if you go to the next slide, I'm sorry, there was an animation there also in this slide and in the next slide, which now would not be running because of the PDF there. But what I want to show there is that you can analyze a structure by changing the stiffness matrix at every step according to the input, what is, for example, for the flexural characteristics and for the shear characteristics, you can calculate the moment curvature relationship, which gives you the change, how the stiffness is varying as a function of displacement. And if you give that as an input, then through the analysis, you can calculate not just the load carrying capacity, but this entire curve, how it is shown on the left hand side. If we go to the next slide, then it's also a similar figure and similar animation, but there it showed that you can identify the damage locations in the structure through such an analysis as well. If we go to the next slide, then we see the seismic demand, which is typically, although the earthquake brings an acceleration time history, we consider this through spectral acceleration versus time period, which we call as the response spectrum. Then if we go to the next slide, then it shows that because if you want to compare two curves, then they should be in the same coordinate system. Typically, the capacity of the structure is given in the coordinates of base shear versus roof displacement, and the demand is given in the coordinates of acceleration versus time period. But it's relatively straightforward to convert it because force divided by mass is the acceleration. So the base shear is nothing but the force. We know the mass of the structure. Once we divide that, we get the spectral acceleration. Typically, it is done for the mode 1 dominant structures. And once you know the acceleration and the displacement, or acceleration in the time period, then you can calculate the displacement, because we know that acceleration is nothing but circular frequency squared times the displacement. So we can relate the time period with the acceleration with the displacement as well. So once you are able to do that, and if you go to the next slide, in slide 19, you can see that you can overlap these curves, and there are certain criteria which you consider to, let's say, to take into account the extra energy dissipation which is coming due to the inelastic response of the structure, and you can get in the end what we call as the performance point. Now, performance point means that at this point you can see on the right hand side figure what kind of damage and at which locations it will be located in the structure. So we can see, for example, the red dots at the base. These are all depicting the flexural failure of the columns at the base. But the flexural failure of one column or a few columns is not going to make the structure, it's not going to bring the structure at the verge of the collapse if it is designed in a good way. So that means if the structure is going to collapse, first there have to be sufficient number of hinge formations, sufficient number of let's say, so damage locations to the extent that the structure can form a mechanism. And typically in reinforced concrete buildings, which are quite redundant, there are many such hinges or many such damages at different locations which should be formed even before the structure can collapse. So then we see the next figure. So in principle, this is a rather straightforward concept, but what's the problem is that even with relatively simple buildings, even with relatively simple structures, unless we have the good models so that we can capture all different failure modes, we will not be able to predict the behavior in a good way. So this is a classic example. This was one test which I was doing within the framework of one PhD, a very simple structure with 4 columns, 4-storied high. In principle, you would say, okay, this is a very simple structure and we can analyze this. But you can see, and these are all the results from various professors from IITs and so on. And we could see that the variation of the predictions was too large, and basically none of them was meeting so good with the experimental results. So if we go to the next slide, then we can see what's the reason. So the reason is basically, I will come to the reason in the next slide. So, but when you want to analyze a structure, then there are different modeling approaches. So one modeling approach could be a detailed finite element analysis that can capture different failure modes in a relatively straightforward way automatically, but it is very time consuming and cumbersome to model. And the other possibility is to generate your own models within the framework of the lumped plasticity approach, which is as shown on the right hand side this frame, where you cannot capture all the crack patterns and all, but you will be able to, let's say, to estimate how much damage at which locations are coming, and then the results would be similar to what you would get from a detailed finite element analysis. However, this is fast analysis. This you can do even at the structural level, But for that, you need good models. So if we go to the next slide, in a typical reinforced concrete structure, the various failure modes, or what we want to capture, or the kind of nonlinearities that we want to capture, they so these nonlinearities include, for example, the flexure behavior, or which is typical for beams, columns, slab, foundation. So columns, because now we are talking about the lateral loads. Then it could have a shear failure, but normally we design it in such a way that the shear would not be dominant. But in principle, it could also be. Then axial, torsion, bond, strut action, so on. And there is one more major failure mode, or the nonlinearity, which might come in the structure, which is due to the beam column joints. And this is a very important nonlinearity, and now I will focus a little bit more on this. If you go to the next slide, you can see a classic example of the failure of a structure, where you can see that the main reason for the collapse of the structure is due to the failure of beam column joints. You can see all these damages in these locations where the beam and the columns are framing into. Now, if we see this kind of structure, the problem, or collapse, the problem is once one joint fails, that means all the connections, so all the connecting members, beams and columns which are framing into the joint, they cannot also function well anymore. So this is one of the major failure modes. And the reason why it is a major failure mode, we can see on the next slide. Typically, if you see the bending moment diagram under lateral load, so this is a typical beam column joint subassembly, as we call it. So which is here in this case, I'm taking an exterior joint subassembly. So which means one beam and one column. And if we see the bending moment diagram, and then on the right hand side, we see the shear force diagram. So I think you all know very well the rate of change of bending moment diagram gives you the shear force. So dm by dx is giving you V. So for a linear diagram, we have a constant shear, but in the joint region, you see the movement on one side of the column is on the positive side, on the other side is on the negative side, which means in a relatively short width of the joint, you have a large rate of change of bending moment that gives you a large joint shear force, which is represented as VJH here. Okay. Then we go to the next slide. So then we go to the next slide, and there we can also see further on that how the shear is coming. So if you see the detailed picture on the right hand side, you see when you have a bending moment which is let's say pushing the beam downward, you have a tension force in the beam reinforcement at the top, which is basically and there is a shear force in the column which is resisting that. And the resultant of these two, that is the tension force in the beam bar minus the shear force in the column, gives you the horizontal joint shear force VJH. And if you divide that by the joint area, then you get the horizontal joint shear stress. So if you go to the next slide, then we see similarly every joint, because of all these forces, there will be some horizontal joint shear and there will be vertical joint shear. If you now take the resultants, you will be able to calculate that there will be one principal tensile stress, and perpendicular to that there will be a principal compressive stress. Now, if the principal tensile stress is in the diagonal direction, then the cracking of the concrete always takes place perpendicular to the direction of principal tensile stresses, which means we will get the diagonal shear cracks in the beam column joint core, as we can see on the photo given at the top. So this is a concrete dominant failure mode, which means of course it is a rather brittle failure mode. So this is the basic mechanics of the beam column joint. So if we go next slide, then we see how we can model the joint behavior in the performance analysis. And there we can see what kind of drifts are coming into the beam and the column just due to the distortion of the beam column joint. So if the beam column joint is distorting, you get an extra rotation of the beam, which will give you at the free end a rotation multiplied by the length of the beam would be the displacement. But this is only and only due to the joint distortion. Similarly, there will be some shear displacement or the shear deformation in the column, which also you can see. So the gamma j is the joint distortion, and gamma j times the beam depth divided by 2. This would give you the column shear deformation, and the joint rotation multiplied by the length of the beam gives you the displacement at the end of the beam. So this means if we have one extra rotation of the beam and two shear distortion of the columns, we can model that through one rotational spring to consider the beam rotation and two shear springs to consider the the column shear deformation, as shown in the right hand side figure. So this is basically a model which you can then make, that you have the member flexure and shear springs, which are basically the moment curvature kind of characteristics for the beam and column. And in addition to that, you have the joint springs, which are considering the nonlinear behavior of the beam column joint itself. Of course, then you need a failure criteria. So this was one model which I developed within the framework of my thesis. And the failure criteria, as we just now saw a few slides back, that the failure is coming due to reaching of a critical principal tensile stress. Therefore, the best is if we give a criteria based on the principal tensile stress, which is one example is shown here. I will not go too much details into this. Also, the next slide I would skip, because this only shows that the criteria depends on how the beam bars are anchored. I would go directly to, I'll go directly to slide 35. So if you are at slide 35, you can see that if you just make this a relatively simple model for the beam column joint, then you are able to capture the behavior of the joint reasonably well. Now, in the graph which are shown at the bottom, what you can see is, if for the lines which represent like no joint model, that means it consider all the nonlinearities. So that means the nonlinearity of the beam, nonlinearity of the column in flexure and shear, but it just does not consider the nonlinearity of the beam column joint. And now you can see how much strength, higher strength, and even more so how much ductility it's let's say you are able to estimate if the joint failure would not happen. But in reality, what happens is the joint failure occurs. So you can see how the experimental results look like. So the experiment is rather brittle, and if you do not consider the joint nonlinearity, you would estimate much higher capacity, both in terms of force as well as displacement, which means from your analysis, it would show that your structure is intact, it is safe, there is no problem. But when the real earthquake strikes, then the structure might even collapse. And this is exactly what we do not want. But if we are able to model the joint nonlinear behavior also in a good way, as I just showed you using this multiple spring model, then we will be able to capture the nonlinear load displacement behavior of the joints, and in the end, of course, structures also quite well. So similarly, in the next slide also similar examples are shown. And then if we go to slide 37, there you can see again for the same structure, which earlier we were not able to analyze so well because no one considered the nonlinear joint behavior. When we only added the beam column joint springs in the model, then we were able to capture not just the load displacement behavior in a good way, but also we could more or less simulate every single failure mode that and every single failure location that occurred in the real structure. If you want to do some dynamic analysis, so if you go to the next slide, then you can just associate a hysteretic rule to that, but I will not go too much into details in there right now. But in principle, it's the same concept. You only, instead of giving a static load displacement criteria, you have to also tell how it can do a hysteretic behavior, because earthquake is a reversing loading. So in the next slide, you can see if you can associate such a criteria, then you will be able to capture even the complete cyclic load displacement behavior very well. Next slide shows with the same modeling approach, even for the dynamic load, like real dynamic loads, as in case of a shake table test, even in that case, you can simulate the structural behavior quite well. And the next slide shows that this was an example for a real life structure, which was in a building in New Delhi, where you could then apply the similar modeling procedures, and you can identify exactly the locations where the failure will occur and which are the critical locations where you should then go and apply strengthening. So if we go to the next slide, now we will talk about some performance-based approach for seismic strengthening. So the next slide says the question that once the structural performance is assessed, and then you come to know, okay, if we need some sort of strengthening, then the next question comes out, okay, which kind of strengthening? Should we use steel bracing? Should we use FRP wrapping? Should we use some local jacketing? Should we use something else, some dampers, and so on? So the answer to that question would be, we should again check what is the performance requirement. So I give you the example in slide 44. Let's say we have the original structure whose capacity curve is shown with the small load displacement curve below, and the demand is given by this response spectrum, and when they do not intersect, this means that the structure is going to collapse. Now, one way to prevent the collapse is if we could enhance the ductility. So that means if we could make some changes in the structure so that even though the strength is not increasing so high, but the ductility increases. So that would be the second capacity curve, which is the longer capacity curve. And there you can see that the performance of the structure is better than what we need, and then the structure is safe again. In next slide 45, we see an example where not only the ductility but also or mainly the strength and the stiffness increase is required, and that we can achieve through structural bracings like seismic bracings. If we go to the next slide, this gives you an example where you can add the let's say the dampers, seismic dampers, which would give you not just a reduction in the demand, but because of the bracing, it may also give you some slight enhancement in the capacity. So then again, you can safeguard the structure. In the next slide, this is an example of what happens or how you can represent the base isolation principles also in this performance-based approach. So basically what we're doing is we are increasing the time period of the structure by adding weak springs at the base. And the next slide, in slide 48, you can see even one, let's say, sort of a managerial approach, which is used for, or which can be theoretically used for rehabilitation of the structures, not for strengthening, but for rehabilitation. So this is saying, let's say, if you have a damage level, as shown in the right picture here, that would correspond to more or less like the life safety kind of a damage performance. And if this building would be a school building or a hospital building, then we would say, no, this damage is too much because we want to continue using hospitals and schools immediately after the earthquake as well. If this would be a residential building for a normal, let's say normal residents, then we would say, okay, this performance could be accepted because we still are sure that the structure is not going to collapse, the people are not going to die. But this is like a trade-off, because otherwise, if we want to get a better performance, then we have to invest more money, and the probability of the earthquake striking is less. Then normally people would say, okay, I can take some risk. So that would be an acceptable performance level for this. So if we just change the occupancy of the building from an office, from a hospital building to a residential building, then we can say the structure is seismically qualified. In the next slide, you see an example where not just the strengthening, but also the weakening. So the selective weakening, as we call it, can be used so that you can prevent some brittle failure modes from happening and you can induce some ductile failure modes. So this is an example where it was a beam column joint with some strengthening. This was also within the framework of my PhD thesis, where we added some knee braces, what we call as the haunch elements, to change the hierarchy of the strength. But still, it was not sufficient to prevent the joint failure. So what we did was, we could not increase the strength of the joint, we could not prevent the joint. So what we did was that we weakened the beam. So by cutting out of 3 rebars, we cut 1 reinforcement bar. Once the beam is weakened and it's weaker than the beam column joint, then the beam failure, which is a flexural failure, is ductile, and then we could achieve high ductility. So that's the concept of selective weakening, that you weaken the structure, but you increase the ductility, because in the end, displacement is governing the performance, not the force. Now, if we go to the next slide, then we start the topic, the last topic, which is the performance of strengthening and anchorages. So if we see now one by one, so in the next slide we see what's the role of anchorages in strengthening. So if we have bracing systems, then of course there is a structure and there is a bracing system. Now we want to connect these two. So how we connect these two? Of course we need some sort of a anchorage or fastening system. So these are two different ways. So either we can do uniform throughout the fastening, or we can go for the point fastening systems as shown in the bottom figure. So if you go to the next slide, again, similar examples of bracing, seismic bracing. Next slide, even for dampers, the same thing, we need anchors always. Next slide, we see the addition of shear walls. There we are adding some post-install reinforcement, which is again sort of an anchorage. If we go to the next slide, again, this is an example through research what we are doing here, where you can add columns to an existing building or an existing foundation through post-install reinforcement. If we go to the next slide, the concrete jacketing, again we need some anchors. Even in the next slide, we can see even for the FRP strengthening, we still need anchors. Otherwise, the connection between the old structure and the new strengthening system will not be established. In the next slide, 58, we can see even for external post-tensioning the same thing. That means if we go to the next slide, the concept is that every strengthening, no matter what kind of strengthening you are using, it needs an anchorage. And the performance-based design for strengthening basically is then reduced to the performance-based design for anchorage itself. So anchorage and fastening is basically the same thing. I sometimes use anchorage, sometimes fastening. Typically in Europe they call it anchorage, and in the US they call it fastening. So, but it's not so easy to design the fastening. Why? This we can see in the next slides, slide 60. So if we see this classic example of seismic bracing, then when you have high loads, then you have high tension and shear forces in the anchors. If we go to the next slide, we see that the concrete will be cracking in these locations because the anchors, when we are installing, we make a hole, we drill a hole in concrete, which act as a notch, and therefore it always invariably cracks at that location. We go to the next slide, we see that there is a limited area to activate the concrete. Next slide shows limited depth to transfer the bond, and the next slide shows that also both the load and the crack will be cycling. So crack cycling means that when the structure is moving left and right, the crack will also open and close. So in this you can see in the next slide 65 also, that when the structure goes to the left and when it goes to the right, some cracks are opening, some cracks are closing. Now if we go to next slide 66, there we can show there we can see one example of a test which was done using seismic bracing connected using post-installed anchors. And in this case, until the anchors performed their function well, everything went fine. But once the anchorage is failed, then the entire system failed as well. Next slide shows the concept of the haunch retrofit. So this is what I was telling you, how the beam column joint behaves. In the next slide, you see a very simple concept. You add some knee braces, which we call as the haunch element, and your bending moment diagram changes. That means the joint shear force are reducing. But when the joint shear forces are reducing, they come at the cost of some increased shear force in the beam and in the column. Now, if we go to the next slide, again, we use anchors to connect the haunch elements to the beam and the column. And in the next slide, or sorry, in the same slide itself, we can see that all these kind of problems like high tension and shear forces, cracked concrete, limited area to develop concrete cones, so on and so on, everything is valid even for this case. If we go to next slide on 70, there we can see the worst kind of problem, that when your haunch is in tension, that means the anchors are loaded in tension a lot. At the same time, the crack in which the anchor is sitting, this also opens to its fullest, which means now it's too high a demand on the anchor because the concrete in which it is inserted, that is opening up, so the cracks are opening up there, so the anchor is moving out, and at the same time we apply high tension force, that means it will have very high demands. If we go to slide 71, we see the example where the same beam column joint, so the geometry of all the joints was the same, material properties were same, reinforcement details were same, and even the design of the haunch element was the same. We only used 3 different types of anchors. So normally people would say, oh come on, anchor is an anchor, we can just insert anything and it should work. But here we see an example where we can see that only because we use different types of anchors in different cases, we got entirely different load displacement behavior and entirely different failure modes, which mean the overall performance of the entire strengthening system depends on the anchorage behavior. If we go to next slide, then we see, okay, we can still evaluate it very well if we have good models. So that means in addition to the structural failure modes, we also have to consider the anchorage failure modes using the, for example, the nonlinear springs, which can consider the anchor behavior. And if we do that, we will be again able to simulate the behavior of the strengthened structures quite well. The next slide shows again similar thing, that if we want to insert a hysteretic behavior, then we only need a hysteretic it's a new hysteretic tool, but for that we also need some new test methods, but this part I would skip for the time being. And so if we go to the next slide, then we see that right now all the design of the anchorages is done force based, which is quite normal when doing the design, but when we do the analysis, then we cannot just go with the forces. That means we need to go to the displacement based design method, which for example is shown in the next slide. One of the possible approaches to consider different springs to model different kind of components of an anchorage and get the load displacement behavior. Another possibility is shown in the next slide, that you make sort of some tests and then you can get equivalent spring for individual anchors, which you can use in the analysis. In the next slide, you see a relatively new and advanced method where you can which is called as the spring model of anchorages, where you can model individual anchor behavior and consider some interactions so that you can calculate the complete load displacement behavior of the anchorage as well. And then if you go to the slide 78, the next slide, then you can, once you have the behavior of the anchorages simulated well using one of these models, then you can consider it as an equivalent spring in the structural behavior in the structural model, and you can see the let's say you can check the performance of the strengthened structure as well, which is some examples are shown in the next slide on slide 79. So you can see the beam column joint. If you use the right models, then you can see whether your anchorage will fail or your beam will fail and what kind of load displacement curve you can expect. And the last slide shows that if you have good models, then you can apply it at the structural level in real life examples also. You can estimate the good failure, the right failure modes, and you can then design an optimum strengthening for those failure modes. And then you can also verify that these failure modes are then, let's say, they are suppressed and the structural performance is improved. So that's all what I wanted to say. Thank you very much for your attention. I know this is not a standard way of doing the presentation. This is also my first time I'm doing like this. So I cannot see at your faces. I do not get some feedback whether it is clear or not. But if you have any questions, I'll be very happy to answer. Maybe it was a little bit too much information in too short a time. But what I want to give you as the final statement is that if we want to analyze or make sure that the structures are safe, we need to go to performance-based approaches. And once we have some good models, then we can estimate the performance of the structure, we can design a good strengthening, and then we can also design the right kind of an anchorage system, or we can choose the right kind of anchorage system for connecting the strengthening system with the structure, and then means we could we could ensure that in any future event of an earthquake, the structure will not collapse. So thank you very much. That's what I wanted to say. Thank you.
Thank you, Professor. Thank you, Professor. Thank you for your valuable time. Even though initially we had a lot of technical issues, but after that we continued a very smooth presentation. There was no lag in that. I think our participants will understand this situation. And a few participants have asked some questions. Shall I ask you?
Yes, please.
From Gokul Krishnan, bracing diagonal and portal bracing, which will be optimum for design, which is safe against seismic?
Bracing once again?
Portal bracing and diagonal bracing, which will be optimum and which will be safe against the seismic?
It depends on your design. So it depends on which kind of failure mode you want to prevent. So if you want to, let's say, it's the same thing as if when you go to the doctor, then the medicine depends on what kind of let's say disease you are having. So if the structure overall, if the structure needs overall enhancement in the strength and stiffness and ductility, then I would say the global bracing is better. But if beam column joint, for example, the beam column joints of the structure are the major problem, then you should go for let's say this kind of hunch kind of elements, which are like the knee braces, because then it's a local problem. So it depends on what kind of problem you want to solve. So if it is a global problem, then you should go for a global strengthening. Then the entire structural performance has to be enhanced. If the structural performance is dominated by some local failures, for example in the beam column joints, then you can go and only focus on those regions, and then again you are safe. So it depends on the problem. That's why it's very important first to assess the existing structure in a good way, so that you can understand where lies the problem, and then you can focus on that problem. Okay.
Thank you, Professor. Yeah. And another question: what kind of damper is used for timber structures?
Okay, I am not an expert in timber structures, but what I can say is, so there are many damper systems, and people use a lot of damper systems, which partly depends on what kind of things are available, what kind of technology is available. So there are elastoplastic dampers, there are viscoelastic dampers, there are tuned liquid, tuned mass dampers, and all kind of things are used. It's difficult to say which one is the best. It depends again on the case-to-case basis, and the principle is more or less the same in every case, that you have some hysteretic energy dissipation through which you get some additional damping. So, but all kind of dampers people are using, and anyway, I'm not a timber expert, but I would say, for example, in reinforced concrete structures also, in general, people use all different kind of dampers. So there's no specific damper which I would say is better for timber or for any other building. Depends on case-to-case basis.
Next question, Professor.
Okay. Mm-hmm.
What is the criteria to improve the strength of a structure by FRP of concrete jacketing?
Okay. So FRP concrete jacketing, the principle is quite straightforward. Basically, FRP acts as an external reinforcement. So if your internal reinforcement is insufficient, then you can add some external reinforcement. Now, the concept depends on which member and against which forces you are going to strengthen. So if you talk about a beam and you want to do the flexural strengthening, then you go for the laminates, which act as a unidirectional, basically external reinforcement. It's nothing but similar to that. Instead of putting the reinforcement inside, you put the reinforcement outside on the surface. But there, of course, then the criteria becomes that how do you connect it. So normally people just use a glue, which is, let's say, an epoxy based adhesive. So if you use epoxy adhesive, which under normally nowadays the new products are quite good, they work well. But if you start loading the beam, then because of the curvature of the beam and because of the inherent stiffness of the laminates, there is a very high chance that the laminate will, let's say, peel out, okay, which is what we call the delamination failure. And to avoid that kind of failure, then you should use some anchorage so that this failure will not happen, because otherwise it will not work again. If you want to strengthen the columns against axial load, then of course, because the FRP is not cannot take compression, so in that case what you do is you use it to increase the confinement. That means you apply the wrap in a way that it will not allow the column to expand, and when the column tries to expand, then this FRP jacket gives the resistance, and in return it provides the confining pressure on the column. There again, delamination could be could be a problem, because again we have all these stresses, and then if the FRP comes out, then again it is not working. So in the concept, the overall concept of FRP is very similar to what you learn in the normal reinforced concrete design. There is nothing so special, except how you need to connect it. So if you just use the epoxy adhesive, in that case you will have to probably limit your stresses to certain values such that the delamination will not occur. Otherwise, you can use end anchorages, and then you can, let's say, utilize higher stresses of the higher strength of the FRP.
Thank you, okay, Professor. Yeah, 2 more questions, is there? Shall I ask?
Yeah, okay.
Is there any lightweight material instead of RCC to avoid the human losses, which is mostly affected by seismic rates like Japan and Indonesia?
Of course, you can go for timber buildings, for example, but then the problem is that they will not be so high rise. Right? You can go for steel, which is always possible, but they have their own problems, their own sort of problems. There are also lightweight concrete and all these things, but I would say it's not so much, as I mentioned several times today, it has more to do with the displacements rather than the forces. Of course, it's good to reduce the mass because the forces are getting reduced, which normally people are doing less. So you can use lightweight concrete, but then your strength also goes down. Okay, typically like 70% we estimate that the strength goes down if you use lightweight concrete. But what we want is that the strength remains same, but the weight goes down. So people, what they do is sometimes they reduce the weight of the structure by changing the material of the infill. So instead of using heavy masonry infills, they can use lightweight bricks, or they can use let's say fiberglass or something like that. But again, coming back to today's presentation, what message I want to give you: it's good to reduce the forces. It's good to reduce the mass, yes. But what's more important is not the force, because if the acceleration of the next earthquake is bigger, your force will again reach that higher level. So let's say you reduce, after a lot of efforts, you could reduce the weight of the structure by 10%. The next earthquake strikes and it is, let's say, 20% higher than, or in magnitude, or in the peak ground acceleration is 20% higher than what you used for the design, for example. This can always happen. This happened in Japan. This happened also in case of Fukushima. It was the same. In New Zealand was the same. So this happens all the time, because you cannot really predict what kind of let's say, peak ground acceleration an earthquake will bring. So yes, it is good to reduce the mass so that your forces will reduce, but you cannot control the accelerations, which means what you can do is, instead of trying to resist, you just try to bypass, which means you go for a larger displacement so that the structure will not collapse and then people will not die. So that means you go for a ductile based concept, you go for large displacements, you go for good failure modes, and then you can safeguard the life of people. So thank you.
Thank you, Professor. And one more question. Is there any option for load bearing structure when it is affected and damaged by earthquake?
Option means?
Maybe
like
he is asking
that they
for
can
a
reuse
remedy.
it. Yeah. So this also depends on how much damage it has taken. Okay. In principle, in theory, in the laboratory, you can even repair and strengthen and retrofit some heavily damaged components of the structure also. In real life, there are many more things. One thing is, of course, also is money. The second thing is the psychology. If you see that the structure is once damaged too strongly, even though if it is repaired and retrofitted, would you like to go there to live again? Probably not. The second thing is the cost effectiveness, that if you have to put too much money into repair and retrofit, maybe it's better to just make a new structure altogether. So if the structure is not damaged too severely, then of course it makes a lot of sense to repair and retrofit and reuse it, which people are doing all the time. But in some cases, the damage is so high that you may not be able to repair or retrofit it at all, technically. The decision what you have to take is, most of the cases where it is possible to strengthen it, possible to reuse it, but whether it is economically viable or not, then you have to take a decision. But mostly, in most of the cases, you can repair and reuse the structures. At least from technical point of view, yes, you can. Okay.
Yes, sir. Yes, fine. One more question. How to deal the junction of column and slab during retrofitting while increasing the column area? I think this is the final question.
Okay. So I guess you're talking about the flat slab connections, right? So where the column is directly going and matching the slab. So again, in this case, most common failure mode would be punching shear. So of course, there also can be some other failure modes. So it depends, first of all, which failure mode is you want to rectify. In many cases, against punching shear, one very good solution to strengthen could be to add post-install reinforcement so that you can increase the punching shear strength. If you have some shear problem, like as in case of the beam column joints, then probably you can also use the similar kind of a haunch element kind of a system. But if it is a flexural failure of the slab which is dominating, then you can add the FRP. If you just want to have the column capital increase, so the size of the column increase, which is like reinforced concrete jacketing, then that's a very good solution. It takes more time and takes more effort, but then again you need some sort of anchorages, post-installed anchors or post-installed reinforcement, which can be used to connect the old concrete and the new concrete. So it depends again on the failure mode. So the most important thing which you always have to check is what failure mode is making the troubles, so that you go and check that failure mode. What people do many times wrong is, it could be that the main failure mode is coming due to the joint failure, but they will go and strengthen the beam and the column using FRP by increasing the strength of the beam and the column, which means the relative strength of the joint is even going down. So instead of making it better, they are making it worse. So the most important thing is to first understand the behavior of the structure and what kind of failure mode is coming. Then you can discuss and think about what kind of possible solutions you may have. Okay.
Okay, thank you, Professor. Thank you for your valuable time.
1 minute,
I want
sir.
to thank
Dayachandran, sir. 1 minute,
our
sir.
management. Yeah. Madam, come, welcome.
Yeah.
Welcome.
Sir, I'm head of department, sir, of EASWARI
Okay.
Engineering
Hello.
College, and thank you very much for sparing your valuable time.
No problem at all. I'm sorry
Very
that because this
informative,
system
sir.
did not work.
No problem,
Thank
sir.
you.
But in YouTube, it has more clarification, sir. That presentation is very nice in YouTube, sir. Sir, one more thing I wanted to have from you.
Yeah.
Because our students of UG as well as PG students, structural engineering, are participating in this webinar. You can also brief about the scope for higher education in your university, how to apply, or what are the research areas if they can go for the PG students. If you can suggest, it will be very useful for them, sir.
Right. Okay. Sure. Okay, so I am working in University of Stuttgart in Germany. So there are many Indian students who come here to pursue mainly the masters, because in general Germany is very, let's say, they teach everything in their own language, which is German, but some specialized courses they offer also in English. You can see on every university's website, either Stuttgart or Berlin or Karlsruhe, all the universities you can see there. Maybe you can go and check on the internet TU9, so that is technical universities or the top universities 9. So these are the 9 top technical universities of Germany, and all of them are very good. The system is really excellent here. And then you can see if they're offering some courses in English, then you will have to apply. So of course it depends then what kind of let's say your they will see your marks in the undergraduate and all these things. They will see your cover letter and some references you will need, some referees from your professors or somewhere. And the good thing is that normally the cost of education in Germany is rather low. So it's not like the US where the cost of education is very high. So you don't need too much costs for paying the tuition fee, but of course the living costs are different issue. For that you will probably have to arrange some funds, or you can also have some mini jobs on the side in the university itself. There are limited seats and there are many people of course who apply, but many of them also they get it, and then you can come here and you can pursue your masters. You can also write your thesis in some companies here, for which you even get some money and all. For the PhD, the system is a little bit different. For the PhD, if you want to apply, basically you should be lucky enough to find a professor who has the funding for the project on which you can work. So very limited funds we get from the government in Germany. We always have to apply through some different departments, which also could be the government department, or we can apply for the industrial funding. So which then, because here in Germany a PhD student is like a normal employee, so the salary, they get a salary, they don't get stipend, and the salary is relatively high. In Indian currency, of course, it's also very high, but even in German system, I would say it's a salary which is more than sufficient to live well and even to support a family. This is more than sufficient. But that means if you want, and it's not allowed to get less money, which means the main thing is that the professor, you need to identify a professor who is working in your field. You may ask him, you can send your application, but mostly I get also many applications. I'm not able, even though I like the people, even though I like the topics they have worked on, but if I do not have the funding of a project, I cannot support, because I don't have the money, and I cannot say, okay, I do not pay you the money and you can come. So that's a little bit different system in Germany with respect to PhD. But the most, let's say, this also brings to a good part. The good part is, if you have the funding with you, almost no professor will never say you no. That means you can already apply. So there is this DAAD, DAAD Fellowship, which I think you probably know. that is for the exchange students. So normally DAAD provides the fellowships which you can use to come and study in Germany. And they also give the similar fellowships for doing PhD also. And if you have that kind of a fellowship, and if you write then to any professor of your choice that I have a fellowship and I want to do a PhD with you, I think everyone will accept you because you come with your own funding. So no one is bothered then anymore from the financial point of view. Of course, they will be guiding you well. That's not a problem. So if you want to come to Germany, I would say one good chance would be after bachelor's. Then you can apply for the master's here, and then you know the system. It's easier to get in the master's in the master system. But if you want to come after the master's to do a PhD, I would say the most important thing would be funding. So if you're lucky, you can find a professor who has a funding, which also happens sometimes. Also in the past, it happened with me that I already had a funding and then one person contacted. So I asked her to come, but this was pure luck. I would say if someone else would have contacted, I would have said to the other person to come because I had the funding that time. So if you can apply for some fellowships, and if you get some fellowships, either so DAAD is one fellowship, DFG gives some other fellowships. Even you can apply for the, I think, Department of Science and Technology. They have some exchange programs, and also if you have the funding, then it's much easier to pursue a PhD. Otherwise, you will have to be lucky to find someone who can guide you. So that's a very short summary. Maybe I was too direct, but I did not want to demotivate anyone. But I mean, these are the facts. So
that's correct, sir.
The best would be if you want to do a master's here. For that, I would highly recommend that instead of going to the US, you can come here. And the good thing is, because in Germany, for Indians, if you have the English medium schooling, you do not even have to do this TOEFL or anything. You can simply say that you have learned everything in English, and then you can simply come here. And the cost of education is rather low compared to the US, so all the things are in favor for masters. For PhD, it's a bit difficult. It's more difficult because of a different system. But otherwise, I mean, this also works.
Thank you, sir. Definitely, this information will help our students also. They will get some idea. Thank you, sir.
Sure. Thank you. Thank you very much. Thanks a lot for bearing with this special type of presentation. I hope it was helpful, and if there's anything, you can please feel free to contact. My contact details are also on the last slide of the presentation, so you can contact me at any time.
Thank you.
Thank you, sir.
Thank you very much, and have a nice day.
Thank you, sir.
Bye-bye.
Thank you.
Yeah, thank you. Bye-bye.
Participants, thank you for your valuable attention, and I think you might have filled the feedback form. Thank you for this session. Tomorrow we will be having another session at 10:30 a.m. morning. 10:30 a.m. morning, and professor is coming from New Zealand, and she will be talking about sustainability in buildings, so that the various categories in our civil engineering field will be covered in this webinar series. So I think all of the participants will be participating in all the series, so that they will be getting a wide knowledge on the various topics. I want the knowledge sharing between faculty, students, and the public, so that this webinar series will be very helpful for new techniques and technologies which is available in the abroad country and can be used in our own country also. So that this is our motto of this webinar series. Thank you for the participation. Thank you very much. And all the participants will be getting the e-certificate after this webinar series. Tomorrow we are going to end the webinar series, and after that it will take a few days to send the certificate to your mail. So kindly bear with this timing. Thank you so much.